Now we're going to go over the types of acids and bases in video 4.1.3. Chances are you won't know the answers to all of these right off the bat. That's okay. We're just going to learn through several examples how to recognize different types of acids and different types of bases. Let's start with HNO2. This is a weak acid. And we know it's an acid because it has a hydrogen right out in front of this NO2 group. And we know it's weak because it's not on the list of strong ones. The conjugate, since it's an acid, is going to give up that hydrogen ion. The conjugate is NO2 minus. In our dissociation equation, we're going to always start with whatever the acid or base is, and then what it dissociates into. So HNO2. Now we're going to draw our arrow going in both directions, our equilibrium arrow, anytime we have a weak acid or a weak base, because when you have a weak acid or a weak base, it doesn't dissociate completely, it goes back and forth in equilibrium. So here, this dissociates into NO2 minus and H plus, and there's the H plus it gives off. So our notes about this one, it's a weak acid, it dissociates partially, and it's in equilibrium, which is why we had to draw that double-sided arrow. Okay, next one. H3PO4, phosphoric acid, is a polyprotic acid. This is a weak polyprotic acid. Poly meaning many, protic meaning protons, so you have H3. You can actually pull off those three protons, but just one at a time. So this is a polyprotic acid. And its first conjugate is H2PO4 minus. Now you can dissociate this again into HPO4 2 minus and just PO4 3 minus to get all the way down to your phosphate polyatomic ion here. But we're just going to do the first dissociation. So H3PO4, and again, since this is weak, it's going to be in equilibrium. And it gives off an H plus and an H2PO4 minus. So this is polyprotic, right? Kind of small for this one. Polyprotic acid, and it has several H plus to remove. They dissociate one at a time. So anytime you see multiple H's in front, multiple hydrogens in front, you know it's going to be a polyprotic acid most likely. Okay, here, F minus. Well, it doesn't have any hydrogens to give off, and it's negatively charged, so it looks like we can easily accept a hydrogen ion here. And so if we're going to accept something, or we're going to accept a hydrogen ion, this is going to be a base. And so its conjugate is HF. That's what it turns into after the acid-base reaction. So the dissociation equation here, or the equation, is F minus fluoride, and that's going to be in water. Now HF, this is actually going to be a weak base right here. This is going to be weak. And that's going to form hydrofluoric acid plus hydroxide ions. So this is your dissociation equation. Anions are conjugates of weak acids here. They don't have H plus at all, so they have to tear off those hydrogen ions from water that's surrounding them. So anions are conjugates of weak acids. So what that means is here we have a weak acid, and the conjugate base right here is F minus. That's just the anion. They don't have H plus. So they must remove from H2O. Alright, next one, potassium hydroxide. You'll know from memorizing this one is a strong base. It doesn't have a conjugate. Your strong bases are not going to have conjugates. So here, your dissociation equation dissociates completely. So KOH goes completely, so I just drew the arrow one direction. It completely breaks up into potassium and hydroxide ions, all the way. So all the KOHs you put in solution turn into K plus and OH minus. Strong base. Dissociates 100%. Okay, not in equilibrium. Magnesium hydroxide. Magnesium hydroxide is going to be a weak base. So you know it's not on the strong list, but it does have these hydroxides here. And they're ionically bonded to magnesium. So your base is not going to have a conjugate here. We have your dissociation equation, magnesium hydroxide. And since this is weak, it's going to be in equilibrium. And giving off your hydroxide anions here, you end up with Mg2 plus 2 OH minus. These don't come off one at a time. The hydroxides come off all at once. This is a weak base, and it dissociates partially. And again, we do have that equilibrium because it's weak. This is a carboxylic acid. So this is an organic acid. Anytime you see like the CH3COOH, you're going to know that that's a carboxylic acid. And this is going to be weak. This COOH group right here, that's going to be the acid part. So the hydrogen that comes off is actually this hydrogen right here at the end. It's not the CH3, because this CH3, these are all covalently bonded. This hydrogen ion here is ionically bonded. So your conjugate is CH3COO minus. The dissociation equation, CH3COOH, and that's going to go to, and be in equilibrium, CH3, COO minus plus H plus. So again, just that hydrogen at the very end came off. So carboxylic acids have the form R, so this is R, so it can be CH whatever. There can be many C's, many H's. R, COOH. So memorize that. Know that that's a carboxylic acid and it's weak. Know that that's the hydrogen that comes off. These are organic weak acids. And if you took AP Bio, you might remember that, because that's important in AP Biology. Okay, the conjugate of that is the carboxylate, and this is a carboxylate base. Carboxylate base. And this is again weak. This is another organic. The carboxylate base has the conjugate of HCOO, and then we have this minus at the end, and it actually turns out that that's where we're going to add our hydrogen ion, right on the end. Just like we took it off the end over here, we're going to add it to the end over here. HCOOH. So the equation for that is our carboxylate plus H2O. It's going to tear a hydrogen off of that H2O to put onto itself and form HCOOH plus OH minus. The carboxylate acid are ions, RCOO minus, they're conjugates of the carboxylic acids. So these guys are opposites, they're conjugates of each other, and they're weak bases. Carboxylate ions have the form RCOO minus. So these guys, again, they're opposites. This is the acid, this is the base form. They're conjugates of carboxylic acids. And they are weak bases. And they're weak bases. Okay, next one. C2H5OH. So this is actually neither. This is an alcohol. So neither. This is an alcohol. So this is an alcohol because you have a hydroxide on the end, and it might trick you to try to make you think, it's a base. But it's covalently bonded to this organic group here. The CH is like that organic group, that R group. So ROH is the form for an alcohol. And so those aren't going to be an acid or a base. They're not going to have either of these. So alcohols, and that's going to be ROH, are not acids or bases. They're their own thing. Okay, next up in the organic section. So this right here, C2H5NH2, this is a base, and it's called an amine. So it's very weak. It's a base. It's called an amine. And that is weak. The amine refers to the NH2 right here. So the conjugate here, if we know that this is a base, is going to be positively charged. When you have an amine, the hydrogen ion is going to attach itself right here to the amine group, not to this covalently bound section here, because non-metal covalent, but over here, you're going to attach to the H2. So since this is a base, it's going to attract a hydrogen ion. So you have C2, H5, and H3 plus. So let's go ahead and write the equation. So starting with my amine, this might take 2 lines. Plus H2O. And then I'm going to write my products on the bottom. And H3 plus, it tore that hydrogen ion right off the water, leaving behind a hydroxide from the water. And that hydroxide in the water now is what makes this whole thing basic. Okay, amines take the form RNH2. And these are organic bases. They pull hydrogen ions from H2O to form ammonium. Okay. And ammonium is that NH3 plus over there. Okay, next up is going to be our acid, and this is just the conjugate. So this is the base, this is going to be our conjugate acid. So this is an acid, and it's the ammonium. Not totally exactly the same as our NH4 plus ammonium that we had in our polyatomic ions, because we have this R group here. But this is our ammonium, NH3 plus. So its conjugate is when it loses a hydrogen ion. So when it loses a hydrogen ion, it just becomes the amine again. So CH3 and H2. It just lost an H plus. When you write this in equation form, you have your ammonium, and that is going to dissociate into your amine plus your hydrogen ion that came off. Ammonium ions are conjugates of amines. Conjugates of amines. And they are weak acids. Okay, next step. Getting out of those organic ones, at least for a bit. HCl, hydrochloric acid, as you know, that's a strong acid. It's Cl minus is its conjugate when it loses that hydrogen ion. This is an easy dissociation equation. HCl is going to just yield H plus plus Cl minus. Notice the one-sided arrow because this is very strong. So it's a strong acid. And it dissociates 100%. and so it's not in equilibrium. Okay, next up. ClO3 minus. This is actually neither. So this is the conjugate of a strong acid. So conjugates of a strong acid, they're not going to go back the other way. So neither, because it's the conjugate of a strong acid. So the conjugate here, HClO3, strong acid. The dissociation equation, it's not going to do anything. Anions of strong acids do not pull hydrogen ions to them from water, so they're not acids or bases. So anytime you have the conjugate of a strong acid or the conjugate of a strong base, it's not going to be either, because you're not going to react the other way to form that strong acid or strong base again, because it would just dissociate completely again. So anions of strong acids do not pull hydrogen ions to them from H2O. They're not acids or bases. Now the next one is really similar, because this, of course, with hydroxide is going to form NaOH, which is really strong. So again, this is neither. This is a conjugate of a strong base. Conjugate of a strong base. So its conjugate then was NaOH. Doesn't have a reaction. Cations of strong bases do not bond with hydroxide, so they're not acids or bases. So they are not acids or bases. Because again, they just dissociate 100%. They would not be able to form this NaOH. It wouldn't stay in solution at all. It would just break up instantly again to form Na+ and not go anywhere. Okay, H2O, as we talked about before, that's amphoteric. Amphoteric means it can go either way. It can be an acid or a base. So the conjugate's either OH- or H3O+, depending. Here, your reaction is H2O, and that's just the auto-dissociation of water, auto-ionization of water. That's your reaction. So H2O can either donate or accept H+, depending on what it's with. What it is with. Lastly, we have HSO3-. So this is also amphoteric because it's the conjugate of a polyprotic acid. So amphoteric. Because it's the conjugate of a polyprotic acid. So the conjugate can either be H2SO3 or SO3 2-, depending on whether it gained a proton or in this case lost a proton. So here, if we're going to look at it gaining a proton, the reaction would be HSO3- plus H2O. And since this is weak, it's going to be in equilibrium with H2SO3 plus OH-. Here, in this case, if we're going to lose a proton, you have HSO3-, and sorry, not plus anything. This is going to directly be in equilibrium to its conjugate base, SO3 2- plus H+. So our notes for this, conjugates of polyprotic acids, here, can either gain or lose H+, therefore it's amphoteric. Conjugates of polyprotic acids, we're running out of space here, can either gain or lose hydrogen ions, and it's amphoteric. Alright, that is the end of video 4.1.2.